If you want to design a retaining wall structure, TG foundation, or even a bridge pier in STAAD, you need to model it using solid elements. Plate meshing is not an ideal choice to model this type of structure. But the problem is, it is very hard to model a 8-noded solid element in STAAD. Also, there is no option available to generate a solid mesh. Using solid elements, it might take days just to create the model geometry properly. Do you know there is an alternative way to model a solid structure easily in STAAD within few minutes? Hi, my name is Surajit Ghosh, and in this video, I will talk about solid elements, different modeling techniques, and how to generate a solid mesh in STAAD using a custom template file. There are three types of element available in STAAD: line element or frame members, plate elements, and solid elements. To model any structural component, which type of element is more suitable? That depends on several factors like the type of load, complexity and importance of the structure, design approaches, and many more. From geometric perspective, there is a thumb rule for element selection. This thumb rule depends on different aspect ratio of the element. If you consider the largest dimension of an element as L, second largest dimension as B, and the smallest dimension, which is normally the thickness, as T, then this rule suggests if the L by T and B by T ratio is smaller than 10, then you should model it using solid elements. As dimensions in all the directions are close, shear deformation needs to be considered during analysis, which is possible using solid element. If L by T is greater than 10 but B by T is smaller than 10, means it has a large dimension in one direction and close dimension in other two directions, then you can model it using frame members. And finally, if both L by T and B by T is greater than 10, which means thickness is very small compared to the other dimensions, then you can model it using plate elements. Well, this is just a thumb rule that many structural engineers follow. But for your project, you are the best person to fix the type of element used in the model. For a shear wall or float diaphragm, thickness is normally very small compared to the other dimensions. So we can easily model it using finite element meshing. But for a machine foundation or a dam structure, thickness is comparatively very high, from just a meter to several meters in few cases. If you try to model it using plate, then you have to assign plate thickness as 1 or 2 meter, which does not produce satisfactory results. In FEA, finer mesh with proper aspect ratio produces more accurate results, and we must avoid a thick element. Also, it is not possible to model it in several layers, as this will increase the modeling time to generate interconnected plate layers using rigid member or master slab, and these interconnected plate layers will not reflect correct structural behavior. The best solution is to model this type of structure using solid element. Instead, we can model different types of solid, from 4-noded pyramid type solid to 8-noded cube-like solid element. Selection of solid type depends on the structure geometry. It is not very easy to model a solid element like modeling a beam or plate. You need to follow the corner node selection order and direction properly, else either the solid will not generate correctly or has a negative volume. Let's check the modeling rules of a 8-sided solid. I am going to use these nodes to generate a solid element. There are 8 nodes and we should start from the front face. Assume that you are looking at the solid. The face in front of you is the front face of the solid and it should be generated first. Just select any node of the front face and then select the next node in the anticlockwise direction. It must be in the anticlockwise direction, else there will be some problem which I will discuss later. Select the corner nodes of the front face and then we need to select the nodes of the opposite face. For this side also, the node selection rule is same. First node must be in the same line with the first node of the front face and then select rest of the nodes in the anticlockwise direction. With this, the solid element is generated. From the rendering view, you can notice a perfect cube is generated which seems correct. What happens if this selection order is not maintained? First, I am going to select the nodes in clockwise direction, in the front face, and also in the opposite face. This time, I have selected the nodes properly, but the direction is not followed. From this view, it seems like the solid is generated properly. If we check the rendering view, you can notice there is something wrong with this solid. It looks like an empty box. The reason is due to clockwise node selection, it is not generated properly and this solid has a negative volume. You can check the same from Utilities, Solid Tools and Negative Volume option. Program identifies this solid and you can repair the solid from here. With negative volume issue, solid does not produce correct analysis results and this must be avoided. Next, I am going to generate another solid by selecting the nodes of the front face in anticlockwise direction, which is correct. But this time for the opposite face, the first node is not in the line with the first node of the front face. Select any node except this one and select rest of the nodes in anticlockwise direction. You can notice the edge of this solid are not complete, it's haphazard. Same is reflected in the rendering view. Does not looks like a complete cube. Moreover, this problem will not be identified from the negative volume option as this solid has a modeling issue. In this case, I have just selected a wrong node in the opposite face and the generated solid is incorrect. From these two examples, you can easily understand how hard it is to generate a solid element. There are 8 nodes and all those must be selected properly following correct order, else the generated solid will provide incorrect analysis result. It is also very hard to identify the problems from the GUI. And imagine that for a dam or foundation model, you have to generate thousands of such solid elements. Yes, it is very hard and also prone to error. Another problem with solid is there is no option available to mesh it properly. You can only create regular size solids without any variation in size or orientation. And if there is any hole, whether circular or polygonal, then it becomes more challenging. Meshing near the hole must be adjusted manually, which is only possible if the coordinates are known. Generation of a 3D solid mesh manually with variable mesh size and with irregular shaped hole is very tough, almost impossible. To solve all these modeling problems and to provide more flexibility with solid meshing, I have generated this user tool. Using this tool, we can generate a solid mesh of any shape in multiple layers and in any direction. This is an Excel-based VBA macro and Several OpenSTAAD functions are running in the background. Let's check how this works. To generate a solid mesh using this tool, first we need to create a plate mesh in the same location. This plate mesh will work as a reference and solids will be generated in the exact same pattern. For example, I want to generate a 1 meter thick solid meshing foundation here with two holes, one circular and one polygonal. Using the corner node information, we can easily generate a plate mesh with parametric model option. I prefer parametric model over the other mesh generator as better options are available in this module, like density line and points are auto-identified or can be defined manually. Also, it is very easy to add a hole anytime using existing nodes or grid. I have already generated this plate mesh, and using this mesh, I am going to generate my solid foundation model. There are few inputs. First, we need to specify the thickness of each layer of the solid. It is better to create multiple layers of solid with smaller thickness rather than a single layer with large thickness. So, for this 1 meter thick foundation, I am going to create 4 layers of solid with 250 mm thickness. I can select the thickness unit from this drop down. Number of solid layer is 4. Next, we need to specify the direction of the solid generation. For this model, we need to extrude the solid in positive Y direction. This information should be provided in the direction field from the drop-down list. Finally, we need to provide information about the plates which will be used for solid generation. Either we can use all the plates present in the STAAD model or few selected plates. For this option, we have to select the plates manually in the STAAD model. And with this input, I can simply click on the Generate tab. If you look at the STAAD model, you can notice that the solids are generated in the model gradually following the meshing pattern. Once the process is completed, the number of plates which are used to create the solid element and total runtime is displayed. Note that runtime depends on the total number of solids generated in the model. If the plate mesh is very fine and number of layers are more, then much longer time will be required to generate the solid mesh. Also, in the output block, STAAD model name and base unit setup is reported. One tip: during solid mesh generation using this code, minimize the STAAD screen. When solids are generated, STAAD GUI always refresh to update the geometry, and this process takes considerable amount of time. If you minimize the screen, then STAAD GUI does not refresh and the entire geometry is updated once you maximize it after the solid generation. So the runtime reduces, and I noticed this reduction in runtime varies from few seconds for a small structure to several minutes for a large model. After selecting the plates in the STAAD model, minimize the STAAD screen and then run this code. Now check the STAAD model. You can notice the solid mesh is generated properly. There are 4 layers of solid and each layer has a thickness of 0.25 meter, which is our input. Look at the solids generated near the hole. It is perfectly meshed, right? Now look at the rendering view. You can notice the solids are generated without any modeling problem. There are thousands of solid elements present in this model, and if you try to generate this model manually, you can neither achieve this type of meshing pattern Also, it will take few days probably to generate the entire structure. Using this tool, we have generated this model in few seconds. And finally, if we check the negative volume problem, there is zero error. The solid meshing direction is determined from vector algebra, hence it is so perfect. After solid generation, you can remove the plate mesh or inactive the plates from the input editor. Another example. This time I want to generate a rectangular bridge pier. For this model, I have generated the plate mesh in YZ plane with proper dimension. This mesh is also generated using parametric model option. You can notice I have included two density lines during mesh generation, one at the pier cap and pier junction, as I want to extrude the pier cap in other direction to create overhang. Another density line at the bottom portion, which I will use later for the crash barrier or pedestal modeling. If you want to know more about the mesh generation using parametric model option, let me know in the comments. Finally, I can select the entire plate mesh and then minimize the model. Open the user tool. I want to generate a 1 meter column with 5 layers, 0.2 meter each. The extrusion should be in the positive x direction and click on generate. The solids are generated within few seconds. Let's check the STAAD model again. See, the entire pier is generated using solid elements. All solids are generated properly, as you can notice from the rendering view. No modeling issue. This solid mesh is perfect for any advanced analysis, and results generated will be much more accurate than a regular solid mesh. We can also extrude partial meshing to create this type of overhang portion of the pier cap or the pedestal portion using solid elements. Using this tool, you can minimize your solid modeling time to few seconds, and if you work in TG Foundation, bridge or dam design projects, then I think this code will help you a lot. Download link is provided in the video description. Just download and start using it in your project. Use the help tab to get more information about this tool or update when a new version is available. If you like this tool or have any feature suggestion, let me know in the comments. Thanks for watching.